Hello, my dear students. Welcome to IK Sir Chemistry classes. In this video, we will discuss the calculation of Racah and Nephelauxetic parameters of transition metal complexes with the help of UV visible spectrum using Orgel diagrams. First of all, let us recapitulate what are Racah and Nephelauxetic parameters. The interelectronic repulsion of free transition metal ion is represented by Racah interelectronic repulsion parameter B. It is expressed in centimeter inverse. The interelectronic repulsion of free transition metal ion is expressed by Racah interelectronic repulsion parameter B, and it is expressed in centimeter inverse. The interelectronic repulsion parameter of metal ion in a complex compound is represented by B dash, and it is also expressed in the same unit, that is centimeter inverse. The Nephelauxetic parameter, that is beta, is given by the following expression. Beta is equal to B dash, that is interelectronic repulsion parameter of metal ion in complex compound, divided by B, that is interelectronic repulsion parameter of metal ion in the free state. Crystal field splitting parameter. The term 10 dq is called crystal field splitting parameter. The magnitude of crystal field splitting parameter, in other words, the magnitude of crystal field splitting of d atomic orbitals in a complex compound, can be quantitatively expressed in terms of dq. Let us see it again. The magnitude of crystal field splitting of d atomic orbitals can be expressed in terms of dq. In dq, d and q are related to some parameters which are the characteristics of the metal complex. Let us see what is crystal field splitting energy. The energy difference between the highest energy d atomic orbital and the lowest energy d atomic orbital of transition metal ion in a complex compound is called crystal field splitting energy. Let us see it again. The energy difference between the highest energy d atomic orbital and the lowest energy d atomic orbital of transition metal ion in a complex compound is called crystal field splitting energy. It is denoted by delta O for octahedral complex, delta T for tetrahedral complex, and delta Sp for a square planar complex. And the magnitude of crystal field splitting is quantitatively expressed in terms of dq as discussed later. Here d is equal to 35 z into E divided by 4 a to the power 5, and q is equal to 2 E R2 bar to the power 4 divided by 105, and multiplying d by q, we get dq is equal to 1 by 6 multiplied by Z e to the power 2 R2 bar to the power 4 divided by A to the power 5. This is the expression for dq, where the terms involved are given here. E is the charge on electron, Z charge on the nucleus, R2 radius of d orbital, R2 bar to the power 4, it is fourth power of the mean radius of d atomic orbital. It means R2 bar is the mean radius of d atomic orbital and it is its power 4. And A, the term A here is metal ligand distance. It must be remembered that delta O is equal to 10 dq. The crystal field splitting energy in octahedral complex is equal to 10 dq. dq is given here. Delta T, that is crystal field splitting energy in tetrahedral complex, is equal to 4 by 9 into 10 dq, and crystal field splitting energy in square planar complex is equal to 17.42 dq. The energy difference between the states of the same spin multiplicity is equal to 15b in the case of free metal ion and 15b dash in the case of complex compound. Let us understand it again. The energy difference between the states, spectroscopic states of same spin multiplicity is equal to 15b in the case of free metal ion, and in the complex compound it is equal to 15b dash. Let us see an example. The energy difference between triplet F and triplet P states of vanadium triple plus having 3d2 electronic configuration is equal to 15b. Vanadium triple plus electronic configuration 3d2, ground state triplet F, excited state triplet P. These two spectroscopic states have the same spin multiplicity, that is 3, and the energy difference between these two spectroscopic states having the same spin multiplicity will be equal to 15b in the case of free vanadium triple plus ion. Now bending parameter, which is denoted by X. In accordance with the non-crossing rule, the N-T1GF, where N is a spin multiplicity, and N-T1GP states repel each other. Let us recall the non-crossing rule. Two electronic states with the same symmetry cannot cross each other in the energy level diagram because at the crossover point the energy and symmetry of two states will be the same. It is against non-crossing rule, and therefore two states with the same symmetry repel each other so that they may not cross each other. As a result of this repulsion, the energy of N-T1GP state is increased by an amount x, while the energy of N-T1GF state is decreased by an amount x. These two spectroscopic states with the same symmetry repel each other. As a result, the energy of N-T1G-P state increases by an amount x, while the energy of N-T1G-F state decreases by an amount x. By the same amount, x is called bending parameter or configuration interaction term. The value of x increases, that is, the bending of these two states increases with the increase in the strength of ligand field. That is, with increase in the crystal field splitting energy. As the strength of ligand field increases, the value of crystal field splitting energy increases, and consequently the value of x, that is bending parameter or configuration interaction term, also increases. Calculation of dq, b, beta and x with the help of UV visible spectrum using Orgel diagrams. If the complex compound of a transition metal ion exhibits three absorption bands in the UV visible spectrum, the above parameters can be calculated. The parameter dq, b and x can be calculated if the complex compound of transition metal ion exhibits three absorption bands. Let us explain it taking example of CrF6 triple minus ion, which exhibits three absorption bands at 14900, 22700 and 34400 centimeter inverse. This complex compound exhibits three absorption bands in the UV visible spectrum, and with the help of positions of these absorption bands, we can calculate dq, b and x, and on the basis of this data we can calculate beta also. A splitting of terms of Cr triple plus in CrF6 triple minus ion. Cr triple plus ion has electronic configuration 3d3. It is an octahedral complex, and the splitting of terms of Cr triple plus in CrF6 triple minus ion will be similar to that in D8 octahedral complex as discussed in the earlier videos. Cr triple plus ion in the free state, quartet F is the ground state and quartet P is the excited state, and these two spectroscopic states have the same spin multiplicity, and hence the energy difference between them will be equal to 15B. The quartet F state will split up into three states: quartet A to G, quartet T to G, quartet T1G F. This splitting is similar to that in D8 octahedral complexes. The quartet P state does not split up in octahedral crystal field. However, it transforms into quartet T1G P state. These two spectroscopic states have the same symmetry. One has been derived from quartet F, and hence it is called quartet T1G F. It is derived from quartet P, and therefore it is called quartet T1G P. Now let us see the energy difference. quartet T2G is below this line by 2 dq, and quartet A2G is below this line by 12 dq. This energy difference is equal to 12 dq, while this energy difference is equal to 2 dq. And quartet T1GF state is above this line by 6 dq. Then this energy difference will be equal to 12 dq plus 6 dq, that is 18 dq. This energy difference is 18 dq. It is the splitting of terms for CrF6 triple minus ion without mixing. According to non-crossing rule, these two states, quartet T1GP and quartet T1GF, will repel each other. As a result, the energy of quartet T1GF state will decrease by an amount x, where x is called configuration interaction term or bending parameter, while the energy of quartet T1GP state will increase by x. And this is the splitting of terms for CrF6 triple minus with mixing. 3 absorption bands are exhibited by this complex compound, and these absorption bands originate due to transitions shown here. The minimum energy transition nu1 originates from this one, and it requires energy 10 dq. How this energy difference is 10 dq? This is 12 dq and it is 2 dq, and therefore this transition will require 10 dq energy. The second transition, this one, this energy difference is 18 dq. This one is 18 dq, and this energy is deducted from this difference, and therefore the second transition will require 18 dq minus x. This amount of energy is required for second transition, represented as nu2. This difference is 18 dq, and the energy of quartet T1GF state has decreased by x, and therefore this transition will require 18 dq minus x amount of energy. And now the third transition, which requires the maximum energy, is represented by nu3, and the energy required for this transition can be understood. This energy difference, this one, this energy difference is 12 dq. 12 dq. This is 12 dq. The 12 dq plus this energy difference is 15b, but here this energy difference will be 15b dash. This energy difference nu3 is equal to sum of this energy, which is 12 dq, plus this energy, which is equal to 15b dash, and this amount of energy, that is x. It is obvious that the transition represented as nu3 will require 12 dq plus 15b dash plus x amount of energy. Thus, the energies required for nu1, nu2 and nu3 transitions are represented here. nu1 requires 10 dq energy, nu2 requires 18 dq minus x energy, while nu3 requires 12 dq plus 15B dash plus X amount of energy, where X is bending parameter, B dash is Racah parameter in complex compound, and dq is crystal field splitting parameter. CrF6 triple minus exhibits three absorption bands in the UV visible spectrum due to following transitions. As illustrated in the earlier diagram, quartet A to G to quartet T to G, nu1, it is obtained as 14,900 centimeter inverse, and the energy required for it is 10 dq. It is obvious from the earlier diagram. The second transition, quartet A to G to quartet T1GF, it is denoted by nu2. It takes place, it is observed at 22,700 centimeter inverse, and the energy required for it is 18 dq minus x. And the most energetic transition is quartet A to G to quartet T1GP. It is denoted by nu3, and it is observed at 34,400 centimeter inverse, and the energy required for this transition is 12 dq plus 15 b dash plus x. All these have been illustrated clearly in the previous diagram. You may see the previous diagram for understanding these terms and these transitions. Now calculations. 10 dq, that is nu1, is equal to 14,900 centimeter inverse, and on solving it, dq will be equal to 1490 centimeter inverse. The second transition requires energy 18 dq minus x, and it is obtained from a spectrophotometric data equal to 22,700 centimeter inverse. On solving it, x equals to 18 into dq, that is 18 into 1490 centimeter inverse, minus this will come to this side 22,700 centimeter inverse, and on solving we get x equals to 4,120 centimeter inverse. We have calculated two terms, dq and x. And now the third transition requires energy equal to 12 dq plus 15 b dash plus x, and it is observed at 34,400 centimeter inverse, and on solving it we get b dash is equal to 826.7 centimeter inverse. And we know that beta is equal to b dash by b. B dash has been calculated and it has been found to be 826.7 centimeter inverse, while the value of B has been given in the table discussed in the previous video, and it is equal to 918 centimeter inverse, and the value of beta comes to be 0.9. There is another question for self-assessment. KCOF3 exhibits three absorption bands at 7,200 centimeter inverse, 15,200 centimeter inverse, and 19,200 centimeter inverse in the electronic spectrum. Then calculate dq, Racah parameter, Nephelauxetic parameter, and bending parameter. Hint: the states for cobalt 2+. In this compound, the oxidation state of cobalt is +2 and electronic configuration is 3d7, and its states are quartet F and quartet P. there is octahedral arrangement of F minus ions around cobalt double plus in this compound KCOF3. Its Orgel diagram D7 octahedral complex has Orgel diagram similar to D2 octahedral complex, and hence the splitting of terms can be represented as here a splitting of terms of cobalt 2 plus ion in KCOF3, which has octahedral arrangement of F minus ions about CO double plus ion, and it is D7 octahedral complex, and hence its Orgel diagram is similar to D2 octahedral complex. This is cobalt 2 plus ion. Ground state is quartet F. Excited state is quartet P. The energy difference between these two states having the same spin multiplicity is equal to 15B. The quartet F state splits up into three states: quartet T1GF, quartet T2G, and quartet A2G. The quartet P state does not split up. However, it transforms into quartet T1GP. Now let us see the energy differences between these states. This energy is 6 dq. This energy difference is 2 dq as discussed in the earlier slide, and this energy difference is equal to 12 dq. Now the minimum energy transition nu1 requires how much energy? Let us see. This energy difference is 8 dq. 6 dq plus 2 dq. It is 8 dq, and x amount of energy is added to it, and therefore the first transition nu1 requires 8 dq plus x amount of energy. Now let us see the transition represented by nu2 requires how much energy? This energy difference is equal to 18 dq. 12 dq plus 6 dq, that is 18 dq. This energy difference is 18 dq, and therefore nu2 will require 18 dq plus x amount of energy. And the most energetic transition will require how much energy? Let us see. This amount of energy is equal to 6 dq. Here it is 6 dq, and this amount of energy is 15B dash. This amount of energy is 15B dash. It is 6 dq, and this one is x and this one is x, and therefore nu3 will require total 6 dq, this one plus 15B dash plus x, that is 2x. 6 dq plus 15B dash plus 2x. nu1 requires energy 8 dq plus x. nu2 requires energy 18 dq plus x, and nu3 requires energy 6 dq plus 15B dash plus 2x. This is crystal field splitting without mixing. This is with mixing. These two states, quartet T1GF and quartet T1GP, repel each other. As a result, the energy of this state increases by x, while the energy of this state decreases by x. These three transitions originate from quartet T1GF. First, quartet T1GF to quartet T2G. Second, quartet T1GF to quartet A to G, and third quartet T1GF to quartet T1GP. KCOF3 exhibits three absorption bands at 7,200 centimeter inverse, 15,200 centimeter inverse, and 19,200 centimeter inverse in the electronic spectrum due to following transitions. As discussed here earlier, the first transition requires 8 dq plus x in amount of energy. The second requires 18 dq plus x, and the third transition requires 6 dq plus 15 b dash plus 2x amount of energy. All these have been discussed in the earlier slide. Now calculation nu2 minus nu1. Let us see. Nu2 minus nu1. If we subtract this one from this one, it will be equal to 10 dq. It will be 10 dq. And this is the value of nu2, this is the value of nu1. It is equal to 10 dq. On solving it, we get dq is equal to 800 centimeter inverse. We have seen that nu1 is equal to 8 dq plus x. On solving, putting the value of dq, we get x is equal to 800 centimeter. And nu3 is equal to 15 b dash plus 6 dq plus 2x. On putting the values of nu3 b dash, on putting the values of nu3 dq and x in this expression, nu3 is equal to 19,200 centimeter inverse, 15 b dash plus 6 into dq. dq is equal to 8. It will be 4,800 centimeter inverse. On multiplying 800 by 6, and x equals to 800 centimeter inverse, and therefore 2x will be equal to 1600 centimeter inverse. On solving it, we get b dash is equal to 853 centimeter inverse. And finally, we can calculate beta, b dash by b. b dash is equal to 853 centimeter inverse, and b, the value of b has been put from the table discussed in the earlier video, and the answer is 0.88. Here the value of x is 800 centimeter inverse, while in the previous problem the value of x was more than 4,000 centimeter inverse. Try to find out the reason behind it. It will be asked in the classroom. Limitations of Orgel diagrams. The Orgel diagrams can be useful in the calculation of crystal field parameters only when the number of absorption bands is not less than the number of parameters to be determined. For the determination of dq, b dash and x, there are three terms. At least three absorption bands should be present. The number of parameters to be determined, or in other words, the minimum number of absorption bands should be equal to the number of parameters to be determined. For example, if we have to determine three parameters dq, b dash and x, minimum three absorption bands should be present in the spectrum. Only then we can calculate three parameters. The Orgel diagrams are mainly for high spin, that is weak field complexes. It is not applicable to high field complexes, that is low spin complexes. Only a spin allowed transitions are considered in Orgel diagrams. In Orgel diagrams, a spin forbidden transitions are not considered. Only a spin allowed transitions involving delta S equals to 0 are considered. These are the limitations of Orgel diagrams. Now, the time for self-assessment. COH2O whole 6 double plus exhibits 3 absorption bands at 8,000 centimeter inverse, 16,000 centimeter inverse and 19,400 centimeter inverse. Calculate DQ Racah parameter, B-dash Nephelauxetic parameter and bending parameter. Solve this problem and it will be asked in the classroom. There is another problem. COCl4 2 minus exhibits 3 absorption bands at 3,300 centimeter inverse, 5,800 centimeter inverse and 15,000 centimeter inverse, and then we have to calculate DQ Racah parameter, Nephelauxetic parameter and bending parameter. Solve these two problems and submit the answer in the classroom. At the same time, another question was given to be considered and its answer will also be asked in the classroom. Thank you for watching the video with patience.